Just let me know once.
Yes, we can see the
Okay,
screen. Yeah.
nice. Okay, so the last session we have had the discussion of Python basics. So whoever tried, I think that would be sufficient for future exercises, which generally involve some machine learning, but that gonna do via help of Python. And if someone who has not tried yet, maybe some weekend or next weekend, just have a look, because the plan is that I'm gonna, over the periods of 2 or 3 months, I'm gonna discuss most important algorithms from both the areas. By both area, I mean supervised algorithms and supervised. And practically, I am also gonna do some hands-on for couple of supervised as well as unsupervised. At least one for sure. So linear regression is one of them. So we're gonna see the theoretical and then followed by in one of the session the practical aspect of that. So therefore, I request that whoever have the lesser ideas of Python, please just do visit it once. Okay, having said that, let's start. Okay, linear regression, but I will not go into that first. I'll just discuss the scenario here. Today in this we're gonna discuss the very first algorithm from supervised learning. Supervised we discussed in the very first session, which means we have the data. I mean, the user provided me the objective that I want to predict the values, the sales price of a house. I want to predict the rent of some locality, some flat in that society or locality. So they provided us the data. So I have the data basically, which are nothing but the futures of the flat belonging to different areas. And here the team also provided me the actual prices of those sample inputs. Okay, this is the configuration, this is the actual price. So basically you got the data, you got the output. So such kind of problem is generally called a supervised, when you have the ground, you have the data as well as you have the labels. Sometimes we call it ground truth. So and such kind of problems are supervised, and we're gonna see linear regression first, because this is the very starting one. It makes sense to start this algorithm. Okay, so agenda would be, we're gonna understand linear regression in a very basic understandable manner. We also gonna see how mathematically it evolved. So how it works basically. I'm going to discuss some functions. Let's not discuss that. Some techniques and some applications. Okay. So whole focus of this exercise is just to understand practically in the fundamental way. That's the goal, and that's okay. So this is how we start. Okay. I'll and most of the time I will keep the examples very simple for linear regression. Let's stick with the housing price data. So how the data looks like to me. As of now, I mean, we can also, just a moment, it would be helpful for me to open the Excel draw, which I've already did here. Okay, nice. Okay, so as I mentioned, when somebody provides me data, the object, the company or whoever we are working this solving this problem for, they also provide me the ground truth, right? This is how the data looks like. Now, data could be of n dimensions. By n dimensions, it means it could have n variables, right? Now, what variables means? The futures. We also called it futures. So I am repeatedly I'm writing these different names so that you guys got used to that. That sometimes we call it dimensions, we call it variables, sometimes futures. Since simple mathematics works, these are different columns. Now, futures could be specific to the housing price data, which locality could be one future, then size of the house could be one future, then number of bhks, that could be one future, is balcony, number of balcony, for example, right? These can be n number of features. And then finally we got the output variable. We call it y, ground truth, also known as ground truth, or we sometimes call it dependent variable, because this is what is dependent on these variables. Therefore these variables also sometimes called as independent variables. So these are some names we also see in one of our slide in past lectures. Now this is how we do, how we have the data. Now this number of columns, number of data could be huge. It varies from at least 1 to n number of, where n is not defined yet. It could be 100, 200, so and so forth. Now for the current understanding, we just take one example. We just gonna see the data which is provided to me sometimes looks like size. This is the size and this is the price, some hypothetical data, just to understand the mathematics and how linear regression works. This is we're gonna see just size, which is our data, input data, and price is the ground truth. Now Coming to that. Okay. Now our objective is we have to predict the prices based on the given information. Now given information is just one variable, which is size of the property. Now I already mentioned what type of problem is this. Now you just need to look. Okay, now the user has provided me the input. User has also provided me the ground truth. So this is a supervised algorithm. So one thing is sorted. Now on the graph you can see, and just stop me at any point of time. These are the sizes of the house. For example, if size is 100 square feet, 1000 feet square, the roughly the price are roughly equals to say 180k, 180k, 180k. And for somewhere here at 1200, we see different type of prices, and these different prices are due to the nature that that could be in some post society, or that could be in some mid-level societies, so some, or maybe some area very far away from the city. Therefore for same square feet the sizes are different, and you so we are on to the same page. So for same size there could be different prices. And if you remember from the very first lecture when I mentioned that it is all about uncertainty. More and more certainty, I mean the knowledge you get from the data, more accurate your predictions gonna toward the input. So this is one example. Currently, since this is just size, we see different varieties, but that's okay. Now we want to based on these data points. These are data points. Maybe if you consider in terms of structural data, these are rows. One data point provided to you, two data points. Maybe these are some set of data points provided to you by the user. Now they want us looking at this data. They want us to create a linear regression algorithm in which once or create a model based on linear regression, that in which we provide the size, it gives us the prices. So this is what we want. Now basically what they want is that okay, this is my input, this is my size, this is my price, right? And they have given some data points. These are data points, and they want us to create a regression line. So I'll explain that in detail. So basically we want to come up something, some machine learning model or some linear regression. Just a moment. We want to come up one line which is well fitted on based on these points. So basically one line on which we create a model. This is a linear regression model, and we want in such a way that, for example, if somebody gives me this input, say size is 3000 square feet, we just extrapolate that, and based on this model we return this point. So we want such kind of lines, regression lines. Now this is known as linear regression. Just on a very layman term, I have explained, given data points, given the in prices, sizes, we want to fit one line to these data points such that when user provided me these inputs size, we extrapolate that, and when it interacts with these line, we return that point. So this is our predictions. Now coming back to the point. First thing first, why it is a regression problem? So that's first question. Why we call it regression problem? So this terms were coined by Sir Francis Galton. What he mentioned is that when suppose for example you take 10 you take 10 students, measure their height. Then you increase the sample of 10 students to 20 students, 30, 40, 50, 100, 200. Over the time, what you will notice, more you increase the sample, the height of them will starts moving towards their mean. So basically, it regresses towards the mean. This is the nature. So for example, takes the example of salary bracket. If we increase the samples of the employee having same year of experience belonging to the same set of niche of the companies, if you start averaging their salaries over the time, they will start moving towards the mean. So from there he coined this term regression. So regression means moving towards to the mean. So this is the term. So this is just an idea I want to mention here, that uh, linear regression. So regression, and now coming to this term linear regression in actual machine learning algorithm. So here the regression word in linear regression means basically we want to find the best line. We want to find the best line that describes the relationship between your inputs and prices. Now see, here this is these are data points. Now it is not possible, to have one line which basically, compare all the points like this way. right? You cannot do that. This is how, so basically there could be the cases where you will, now this is one line. Now there could be, some model trained on these data points and the model line came out to be this way. Now this could be one case. Let's take it another color, this way. Now for example, there could be line that could be surpassing these points like this way. Now these are different lines which is keeping the relationship of size and the prices. Now linear regression helps us to find the best line, and the term they use is that they want to find the best fit line. So basically the line, a line in this example, a 2D line which basically is the best fitted, I mean captures the best essence of these data points. Now if now these are some 100 points, now there could be, when we work in real example, the points could be like 10,000, 2,000, right? So you can assume that if data is provided to me, now suppose these are the data points and the points are say 10,000, so these points would be spread across all the data points. Now you can assume that indefinite numbers of line can be created, some line passing this way, some line passing this way, some line passing this way. Now how you will decide that which line is the best fit? So hey, always remember best fit is means, so it is not always possible that one line compresses all the points. This is how the model do not work. We want to find the best line which is able to capture the best fit out of these data points. So how you do that? Now at least we come up to this point. Okay, I want to find the best line here which would be passing from these points, and these lines would be best fitted based on these data points. Now coming to the second question, but how you can assume that? So before going that, let's see here in general how the data you're gonna see in your data set. You would be having the,
Raj, one question.
yeah, please.
Yeah. So, so if I understand correctly,
Hmm.
the model will always expect a straight line, right? So you mean to say there won't be any
Not all.
uh,
So
or
I got a point. Not always. Not always. Yeah. So you mean to say,
because
if there are data points, but will it always be straight line? No. But right, there could be the point that model could be like this way, line could be this way, right?
yes, exactly. Yeah.
This could be this way. But right now I'm just focusing on the basics of linear regression. So just be with me. Assume we are just fitting a single straight line, right? So
Okay.
I will come to this point here. So, but again, let's not jump, not jump there. But let's now assume that we are just fitting a straight single line, linear regression, right? Just assume with okay, how the
So
line takes
there is
this
another
shape.
Hello,
question.
hello.
Yeah, yeah.
Can you please repeat the significance why we are doing? What is the need of state means linear line? Uh,
Why we are
means
doing a linear line, right?
means what is the outcome
Okay,
of doing this?
okay. So did you understand? Just a moment. Did you understand that what problem we are solving right now here,
Yes, the
right?
size and model will give
Side,
us a
yeah.
price according to
This
the
this
size.
this is a very toy example. In real life, you would be having n number of features, right?
Yes, yes,
N number of features, and that between n dimensions. So you can even remember with that fact that in n dimensions you cannot have a n straight line. It would be a plane, right? So
yes,
for example, right, so just be here, why we are doing that, we are trying to understand our linear regression model here, which works on structural data where you got the input, you got the output. Now this is a very toy example. There could be the cases where you are trying to find that how long in future my machine will work before a breakage. For that you got the futures or parameters of the machine, or for example, how long this conveyor belt gonna be there in the future in the production line. So output would be, it is expected to run 3 years from now on. So that's output. And what could be the input? Input could be very thing. I mean, it was, the last failure happened 50 days back. It's still running from 30 days. So these are the futures. Now your objective is to find. So basically, when you use linear regression in supervised, you
yes,
use linear regression when you want to predict the continuous values. So let me mention this right here. I want to predict something. So basically I want I we want to predict output as continuous values. So for example, predicting the house price, that's your continuous data. By continuous you mean the numerical values, not yes or no, not in classification binary 0 1 2, or not in discrete form, whether text. So we are dealing with continuous values. For example, 20,000 point 0, 20,000 point 1, 10,000. So continuous data. Some other examples: salary of an employee, right?
Yes, yes.
Durable. So you got my point. So first thing first, when we are supposed to predict the continuous data based on the input, linear regression is one of the method, right?
Okay. So we have
Okay,
to train our model that way. Means
that way. There are
okay.
multiple models. There are multiple models. So eventually, multiple algorithms, not models, we're gonna see in supervised learning. But we start with linear regression because this is the most basic one and most fundamental in nature, right? And by, as I
Thank you.
mentioned in today's mail, by understanding this, the next few algorithms will become, this becomes a benchmark for that. And this is very easier. Now, sometimes also happens, it's just not about model training, it is also about how faster your model trained, because we are working on lakhs of data input. And if I want my models to be trained within hour, so what is the number of computations, what is the cost? So that is also takes in picture. Linear regression is very faster. So that I'll discuss in benefit. I mean, when to use linear regression, what is this benefit in terms of other supervised algorithm. But now we are just discussing it as our very first algorithm because it's very easy to understand. So let's keep things very easier. Start from very basics, then move to a difficult one. Okay.
Okay.
So coming to back, a simple thing here. We have data, which again in which there are some data points as mentioned, right? This is data point, and I want to fit one machine linear regression line. Now this could be this line, this could be this line, so on. Generally, I use pad, but I'm still not pad to draw. But I am still not in Pune. I was supposed to reach there by 7th, but now I reach on 14th. So next class I would be using pad, so things become easier for me too. So just bear with me today's session. Okay. Now we understand that we want to predict some real valued values or continuous data. Now, looking at this data, there could be n number of linear regression models you can build upon. By which I mean n number of linear lines. This is, so that's okay. This is how your data looks like in Excel. Sometimes you cannot get data in some source. They would be providing structural data in Excel way. There would be size, etc., columns, and then price. This is how. In future, I'm gonna refer the term these things as X. These are my input variables. When I use term Y, that always means the ground truth, actual values. And when I use M is nothing but the number of rows. So if I say the training data is M equals to 1000, which means we are talking about 1000 rows. So this is a standard. Okay. Now see, let's try to understand that. We have the training data. We already show. Now basically we want to come up with some kind of algorithm, in our case linear regression based algorithm, in which I provide the size of the house, and finally the output of that would be y head. Now take it with the session which I discussion that we do not know what is the actual function, because we do not know what all future it is supposed to take. So we want to come up with some hypothesis, also called as function, which helps us to find the size of house given giving the predicted price. How you can calculate this hypothesis? Linear regression is one of the example. So eventually what happened, we gonna come up with some function, as I mentioned in the first class, which would be y hat. We also call it y hat, generally a kind of hat on top of y. Y hat is nothing, it is just a function which will try to you know go closer to the approx of actual y. you know Actual why we do not know, because that's why we are solving this problem with machine learning. Would it have been just sine wave data spread in sine wave? You could just straight away apply the sine wave. But what is actual function that we do not know. Therefore, we are creating a machine learning solution. Machine learning solution looking at the data helps to calculate y hat of a approximate function, which would be closer, which will try to be closer to the actual y. Therefore, you would be creating multiple lines, and finally, what we want, we find the best line whose output is closer to the actual y. This is our target. So therefore, we want to find the best line. How we do that? That is our gonna be our concern or the topic. Okay,
Sir,
coming to,
how is
yeah.
it different from line fitting? We have curve fitting, right? Where we try to fit a linear line in
Hmm.
or any other curve also. So how is it different from that?
So again, this is the same question asked earlier. There could be line. So this, so if you straight away want to know the term, the thing which I'm discussing right now, this is linear regression. If we want to find the fit the curve, that comes under the category of polynomial regression. But just I want to understand, I want to tell you the mathematical function, how we derive that thing. Therefore, I'm just taking it the simple linear regression, right? But if you want to fit a curve, then we can fit a curve, but that would be called as polynomial regression, which is an extension of linear regression. Now it comes with caveats. When polynomial regression works better or linear regression, we gonna see that, right? So
Okay.
does it yeah okay. So yeah, of course it is doable. It is different. Now how it is different, let me also answer that thing. In, as you mentioned, polynomial, so they, if we are doing a quadratic, so polynomial could be x power is 2 3. So n depends on polynomial n. So if I'm just fitting it as a quadratic line, then my output will why it is not changing the color. It would be something fit like some quadratic. Now this could be one of the quadratic polynomial. This could be one quadratic polynomial, right? So if it is polynomial, it is raised to power 3, it could just straight away go, right? It depends. But right now, let's not complicate the thing. Keep it very simple. We are trying to understand the mathematics, how to find the best line. So linear regression is easier to understand that thing. But then eventually same concept can be generalized to linear and n number of polynomial regressions. But now the main, even you should think that, see, they are just 10 points, but if they are 1,000 points, you can assume that there could be infinite numbers of line. Which is better or which is more closer to the actual y. That is the target. That is the task. And linear regression algorithm helps us do that, to find the best line. So my next goal is to understand that part, how to find the best fit line. I want to say one more thing. Linear regression is just not creating a line. It is the algorithm. Just remember, just focus on this point. It is not the way of creating a line that you can just do with y equals to mx1 plus nx2 plus c, just straight line formula. Your goal is to find the best line. That's what linear regression helps us to. So do not consider it just creating a plain line. It's is to find the best line. So take this example. Coming to that, let's formalize this example hypothesis. There would be some, suppose we are dealing with some line. So I think everybody knows that the equation of single line is y equals to mx plus c. So here so x theta 1 is the coefficient of x, theta 0 is some intercept. By intercept, so here, so for example, if my line is going, for example, this is my line. So this part would be your intercept, and this slope, the slope would be your slope at theta 1 coefficient, mx plus c in terms of quadratic. So this is my equation. This is your general equation. Now you can have, now you know, so considering this point, you can have theta n number of values in theta 0 theta 1, which will give you one line, right? So considering again here, right? uh, Suppose these were my data points. Based on these data points, this, suppose initially somebody told me, say choose theta 0 equals to 1.5, theta 1 equals to 2. That set of theta 0 theta 1 gives me this line. Now suppose somebody told me, now say take theta 0 equals to 2, intercept equals to 2, and slope equals to say 3.5, for example. Now that will give me a line, say this line. Now you can understand that why changing the values of just theta 0, theta 1 or both, you are getting one line. So how this boils down to, just consider fact, we want to find the best line, right? Goal is to find the best line. Within 10-15 minutes, everything will start coming, make start proper sense. We want to find the best line. Now I give you example, theta 0 and theta 1. Let's change this value and we get one new line, right? So this means just by changing theta 0, theta 1, we can get infinite numbers of line. Now I want to find the best line. So for that, what I want to find the best set of theta 0 and theta 1. So now this is how we boils down our problem. Now my problem boils down to best line would come up by the best set of theta 0, theta 1, right? So there exists in universal space, there exists some theta 0, theta 1, which fits this line best, overall best, with respect to the data given, right? We need to find that theta 0, theta 1. Now just tell me first, let me come to you guys all, if this is making sense, the concept of theta 0, theta 1 and the best fit. It would be helpful if anyone, for all, just answer me,
Yes,
right?
yes, it makes
Okay.
sense clearly.
Yeah,
Yes, yeah.
and please stop me whether it doesn't start making sense, because I have to just keep things slow, simple before going to the difficult part. Okay,
So
so
sorry,
yeah,
sorry,
yeah,
just to double confirm because we were just talking about that. The aim of the linear regression model is to find a a straight line, a best fit straight line,
right,
and the y hat is the prediction. It could not be the actual one, but it is the best possible prediction. And using the like theta one could be like the slope, right? Like
yeah.
how
In
is
this
the
case, yes.
yeah, in this
In this
case,
case,
yes.
yes,
And then
yes.
the theta zero would be like the like the y intercept or something,
Perfect.
which
Right.
will okay. So it means, so that is what is our confusion. Like how different is it from like curve fitting? So even in
Of
case of curve fitting, we will
uh,
have a
yeah, yeah.
so even in case of a curve fitting, we will have a set of data where we will try to match or you know try to get a
So
best curve. Let's say if it's a
okay,
linear, then it will be linear. Uh,
okay, I got your point. So I'll just answer it one line. Let's not discuss that discussion ahead. In your case, in in polynomial regression, in curve fitting, instead of having x1 or x2, there could be the cases you're gonna see terms such as, for example, q3 dot x1 raised to power 2, right? These terms will start appearing up,
okay.
right? See, you can solve a problem, I mean, by spending some money, or maybe a larger money. My point is that if the problem is getting solved with lesser computation, which one you choose? You always choose go with the
Lesser competition.
lesser computation and lesser time. So for example, if you are solving a problem, it is taking me 6 hours of training, right, with with say polynomial regression, and I get some accuracy 90%, for example. Now same thing, for example, I am getting linear regression pretty much faster than polynomial regression with just 2.2 hours, approximate accuracy of 87%. Then I'll discuss with business, and again 6 hours of training, 6 hours of system running, computations happening, that's the cost. So then I'll ask with the I mean the business translator, business objective, which one you prefer. Overall this makes sense, right? So point is that we start with the basics. If things are getting solved with the basics, then why to go for the polynomial regression. Also, it's not always the case you can easily fit polynomial linear regression. I mean, even these points are spread this way, and you think of applying polynomial regression, that nature has to be there in the y. I mean, it's not always the case that bc point is spreading across all, we just fit the polynomial regression. So that's the kind of hyperparameter tuning or the parameter tuning you're gonna do in the future. you're gonna see. So this is what this is how you do experimentation in machine learning. Your first solution will not directly work. You will do a different sets of solution. You will evaluate on the test data. Okay, linear regression is working well. I'm getting good results with the polynomial regression, and then finally decide, let's go with the linear or polynomial based on all the caveats, right? But technically this you will start seeing terms such as this: x1 raised to power 2, maybe some x2 raised to power 3, right? And think practically. I mean, when I mention this thing, let's if this topic has now started, let's take 2 minutes here. If I mention here, can anybody tell what it signifies practically, considering the housing price solution? Can anybody explain me what does this term means? Do not think it as a quadratic term here. That's mathematic aspect. But in terms of pure layman term, what does it mean?
So if something changes, some variable changes, it will change
That that
into square terms. So output will
that
change into square
mathematics
term.
that that
Okay.
that, that mathematics from practical aspect, what in terms of the way I am explaining size of house, think in that way, what it makes sense.
Okay, like the prices are doubling or squaring over the period of time. Something.
Take it this way: if x1 is just number of rooms in a house, 3 bhk 4 bhk, right?
Hmm.
Right. So if I square that, will it practically helps you get some knowledge, or
Uh,
model will start better? Okay, this is 3 bhk house. If I just make it 3 square 9, so my model will start learn better with this aspect of squaring. No, so it means there's no sense of the
yeah.
squaring the term such a house. So the nature of data also has to be in that way that the squaring of that makes work, right?
Okay.
let me
Yeah.
let me give an example. I already give you an example. For example, I have this data size itself. I mention you that 1500 is the square feet, right? But I also, let's straight away work with the size. But somehow I have not this data with me. I have some data, for example, 3 rooms, BHK. I also have the size per room, for example, 486. Now this is X1 feature, this is X2 feature, right? Now, if I create a new feature, overall size, what it would be x1 dot x2, right? Eventually you are getting the same information here, but right now this equations or this variable become polynomial, right? But the information, think in terms of information, the overall size of this house, that was even eventually coming with just this variable as well. So my point is that we use polynomial regression where it makes sense, where the squaring of some of the futures makes sense, that it helps me learn better better prices in our example, right? So this I'll come up, I mean, this will come up when polynomial regression makes sense. That would be the ending of linear regression, right?
Yes. Understood. Yes. Yeah.
Okay, so yeah, actually mathematics is very easier with linear regression. Otherwise, it involves differentiation. If I use x raised to power 3 4, then our differentiation becomes little more complex for the part will become difficult then. But overall, everything works same. Whatever you're gonna do with the linear, the same way you're gonna do with the polynomial. Just we need to learn later that when to use polynomial regressions, when it makes sense to use polynomial. Okay, coming to the fact now, if I think everyone now agrees with me that theta 0 theta 1 is our goal. We want to find the best set. Now, for example, I'm not able to write it here. For example, suppose somebody provides me later, somebody provides me one more feature size. Somebody provides me is number of balconies, right? Feature in terms of 1 2 3, right? So here this is theta 0 intercept, theta 1 is your coefficient associated with the size. I want to show you how y hat looks. Y hat, right, also called hypothesis basically. So this is some intercept, let's call it x0, some coefficient theta 1 associated with the size plus theta 2. Now this is how equation will change. Theta, this is just theta, not q. Always remember theta 2. Theta, it could be anything, c1 c2, but here we are theta 1 referring to some coefficients associated with the size. Theta 2 associated with the number of balconies. So now we are dealing with two coefficients. So this way, if we keep increasing the futures variables, we increases the coefficients. Now you understand that why it is easier for me to just use one variable just to for mathematical aspect, nothing else. So our goal is to find best thetas. When I have n futures, still the goal would be find best thetas. Thetas would be theta 1, theta 2, theta 3, and so on. Coming to that. Okay. So theta 0, the best theta zeros, or the will give help me find the best line of fit. Remember the word, it is best. It is not always true actual. It will always be best. It's depend how they are, all of you are working, all of you are working, creating a different machine model learning. Someone's line would be best with them with her or with themselves, but one of you guys lines would be better than others. So it's just about best. It is always relative, remember, right? Okay, let's boils down. Now my objective is boils down to just find the best, choose theta 0, theta 1 such that s theta x, also called as hypothesis, also called as y hat. So let's not confuse, it is y hat, close to the actual y on our training examples, right? These are 5 examples. So I will not go ahead. I still want to draw one picture here. Mm, And now this will start making sense now. Again, same here. Suppose in this toy example, we have these 5 points. Simple 7 8 points. Now you will see, okay, this is the points. I based on these points, I find the best theta 0, theta 1, which comes out to be this way, right? Now next day the business translator came to me and they say, hello, these I am just giving you 10 more points, right? That guy gave me 10 more points. The point which he or she gave me, that was somewhere here. Now you see, give that now the data is increased, the best line fit would be changed. It would be somewhere now this way. See, so it's always data. Is always data. More the data you get, more the better line you will receive. You know, whole context of linear regression finding the best line changes because I get the more data points. Now I want to find that set of theta zeros which is best fitted among all these 20 points. So this is how our theta 0, theta 1 changes when we get the new data. Therefore, it is always said, some of you must have heard that when you give me more data, I'm going to train my model again. That model will give me new model object, which would be better. Mostly it would be better. Yeah. So if that part is clear, again repeating myself, choose theta 0, theta 1 such that y hat is closer to the actual y. Now consider, take this point. These are my these are my data points. Let's draw it bigger. If it would have been bad with me, things I should not, I would be drawing a little better. But okay, point 1, point 2, point 3, point 4, point 5. Let's keep it very simple. 6 point. This is our line given by some model. Forget what is the model. I trained my model. It gave me theta 0, theta 0, 1. Now the intersection. These were the size, right? So this is size here, right? Here we got the price. Now let's take this line. For this size, this is the actual, right? This is the actual. The actual price is this one. But for for same what I get, mm, for same what I get the predictions, I got the prediction this. This is for this. Extrapolate this point here, this, right? These are the predictions given by the model. For this, the prediction given by this. For this, predictions was this. For this, prediction this, and this. Now see, and these are data. These are the size. For this size, predictions was this. However, the actual price was this. So there could be the cases when the prices are predicted lesser or more. Let's do one thing here. Join these lines. This is to understand something. So let me join it first. Oh, right here. Last join. No. Okay, now question to you guys. uh, as of now, uh, just a simple question. um, what do you think, what if this line, I draw some line considering these green bars, what should be the what should be the case that if I sum up these lines, whether it will increase or decrease if the lines is best fit. Repeat my question again.
Yeah, can
Suppose
you
the,
repeat?
yeah, so just again cursor here. uh, this is the output, predicted values. These are orange dots are the actual values. So green line which you are seeing is nothing but the absolute difference between the actuals and predicted values. So these are the 1 2 3 4 5 6 data points. These are 6 bars, which is basically the absolute difference. For example, suppose this is 100, suppose this is 200, predicted value is 100, so difference is 100. So now if the line, there are two lines, suppose line 1, line 2. Out of line 1 and line 2, which one would be the best line, which is having the difference lesser or more? Let's write this question, and it's would be easier
Sir,
to line.
difference.
difference
Difference is lesser.
difference is lesser, right? Because lesser the difference, mm, uh, just think with your mind. Lesser the difference, more closer my line is to the points. Overall, I am talking about overall, right? So lesser the difference, what we want, lesser the difference. Okay, now tell me one thing. This is 100. Suppose I take the difference this way, y minus y hat. Let's keep it this way, since as of now we are uh, so first thing, does everyone okay that difference has to be lesser?
Yes, of
Okay,
course.
perfect. So
Yes. Yeah.
suppose this way we are keeping this absolute difference with keeping y first. So here y is 200, right? 200 minus y hat saves 100. So difference is 100. Suppose this example, this is, or just to make mathematics, this is 300, actuals for 300, this for 200, predictions difference is 100. In this case, suppose actual is 100, this one, this dot, predictions is 200, this comes out minus 100. Suppose we do it for all the points. Don't you see, I mean, these differences now are negated, right? So what does it saying for these 2 points? The total error or total differences just comes out to be 0 for these 2 points. For example, if I'm saying total difference is 0, practically it means there is no green bar. I mean, there is no difference between actuals and true. So don't you see that? Does it make sense to keep the absolute? Did you get my point?
Yeah, yeah,
So
Yes.
yes.
there has to be something, some better way of finding the differences, right? Now do it one thing, just for my function. What if I do it square? For example, so this 100 becomes a square, this becomes a square. Eventually, eventually the negation is removed. So you would be getting some errors, which should be in forms of square, but they they remove that biasness or that aspect of, if actuals is lesser than predicted or predicted is lesser than 1. So just for an idea, absolute difference will not
So
make
it
sense. Mhm.
so it should be y square minus y hat square, right? Not the
No, no,
whole.
no. No, no. I'll come. So y square minus y hat, no, I'll come up to the thing is always should be y minus y hat square, because
Ah, right. Sorry.
yeah, right, a square minus b square would be then a plus va minus b, which are not making sense, right? So, but let's not jump y square. I just give you one example. That notion I want to explain here is that why just not keeping the plain differences is helpful, because it will negate, it might negate and will not give you the right picture. So let absolute errors, good way, but not the appropriate way. Coming to back, right? So
Why absolute is not appropriate way? Because in that also we are
excluding the effect of sine. So that is
No,
our
no. How? Let me explain. This is absolute, right? And
yeah,
this is for data point one. We get 100, right?
yeah,
For data point two, we get -100.
yeah.
Sum up both errors, both
No, no,
data
no, no.
data
What
points.
I'm saying that second minus 100, now we can just take absolute value. So will not that work if we take just absolute value rather than squaring it, both the
But
terms?
I mean, this is one of the best. I mean, this is a very good question. You want to see? Let's do this way, right?
Yes, yes, yeah,
Yeah,
yeah.
we could have taken this thing, but if you check, I mean, you will see in the future, differentiation doesn't exist for absolute functions, right? You must have heard the term differentiable, right?
Differentiation, differentiation.
Dy by dx we used to do
Okay, differentiation. Okay.
differentiation. We cannot do
Mm-hmm.
differentiation of absolute functions. Not
Okay.
possible in mathematics. You know,
Okay, okay.
that's one of the drawback with us. Not drawback,
Okay.
limitations. Otherwise, very
Okay.
pretty. So everyone, what he mentioned is that let's why taking the absolute, just do that, make this function like this way. And I will later you will see why I am talking about differentiation here. He was saying that let's do it this way, and perfectly makes sense. This is 100, this also becomes 100. So we now 200, we are not negating the effect. We could have taken this thing, we could have taken this thing, but unfortunately you will see during the mathematical derivation, we at some point of time we will do the differentiation, but you can check the differentiation of absolute function is not there, because this is sort of a step function, for example, not step function. So absolute graph, if you remember, or if I draw absolute graph, sometimes looks like this. I mean, this is how absolute graph looks, right? So for this value, the value would be this. Even for negative value, the value would be this. So this would be the graph, and this thing is not differentiable at x equals to this point,
Okay, got it, got it.
right?
Okay.
So this
Yeah,
is
yeah.
the
Makes
drawback,
sense.
but very good question. Yeah.
No, sorry, can I add one point here? Like,
Yeah, sure.
so what I understand is, like if you can go scroll up to that.
Mhm.
So, like if I try to just trace the path of that point. So, like one point is on the positive side of the blue line or the ideal line, and the other one is on the like the negative side. So,
Mhm.
because what we are trying to do here is we are trying to trace a straight line, but rather the actual point data points are varying, right? So the green
Right.
lines represents the shift or the delta from that main blue
Perfect.
line.
Yeah.
So
Mhm.
what happens if we directly straight away take without any effect is we are essentially just shifting all the points to one side of the curve. So we don't know how the behavior of
This
each
no
point
no.
is happening.
So your assumption that we want to bring all the points to one side, that's not right. So
No,
why?
no, that's what I'm saying. No, no, exactly.
Hmm.
So that is something we should avoid. So that maybe that is also one other
No, no.
reason that why we should not do directly take a negative to positive. So
So
what I'm saying is
hmm,
we should square. Like squaring will give that benefit what you mentioned,
hmm,
like the
hmm.
differentiable for sure. And then the other aspect is uh, we are we can still we can still keep avoiding the shift of one point. Like because for example here you yes, that point, yes, exactly, that
Hmm, hmm.
point is on the other side of the plane or
But
other side of the line, so we don't.
I understand your point. I mean, your that point is okay, but still we are not shifting any points by taking the absolute. You are just taking the absolute for the mathematical aspect. I mean, see, what I mean to say here is that let's keep this example. This part is -100, right?
Mm-hmm.
This part is 100, and
Mm-hmm.
then there are one more line, suppose, which is somewhat going like this way. So for that, the difference is this part and this part.
Yes, yes, yeah,
What I want to see is that I want to fit the best line for which overall error is reduced.
yeah,
Overall errors are absolute errors, not the negative ones.
yes,
Because
understand, yeah.
yeah, so anyway, if I do this absolute, we are not shifting the line. Lines are not shifted. It's
No,
just
no,
that
I'm not saying like the point which is below the blue line. So
it will not
you're
shift. Only see, this is just this is way of saying that how much there is an error. Now there could be different parameters. You can
yeah,
define error in terms of square, you can define errors in terms of absolute, but error is error. So for example, uh, if the error is here is 50 at the level of absolute error, somebody somewhere the error is 30 at absolute level, 30 is lesser than 50 in terms of absolute. But in terms of square, the error is still, if the error would be 50 square, which is roughly 2500, then 900 is still, 900 is lesser than 2500, but I cannot compare 900 with 30.
yeah, understood.
So yeah, only this would be little easier. But again, and one more aspect here is that important point is differentiability. Second, also absolute are the costlier functions, which which is the inherent nature. Second, but main
Yes.
point, main cause of concern is differentiable. At some point of time, so have you heard of, I mean, everybody, have you, when we studied differentiation during 11th 12th, we used to differentiate to find the lowest minima up, right? The, you know, we always try to find that. So I'll come up later, but okay, let's not go in that direction. But as of now, one of you told that let's take absolute. uh, we also discuss, let's say square. Somebody can say why square, let's take cube for example, but again cube becomes negative. So let's say power 4. There could be an analogies we can give. We can each can have one analogy. Our goal is to find the best analogy here. So okay, so absolute part is done. Let's come back. So now this part is created, green parts are understood. Okay, this is for time being. Again, to make things easier, I assume my best fit line is passing from center. Again, this is an assumption because to make the mathematics easier. But in practicality, again, suppose my best fit line is such way it passes from center. Why I'm passing it from center? To avoid working on theta 0, make the intercept 0, right? So if I make the intercept 0, what will happen? Theta 0 will disappear. Now you could say why making theta 0 is 0. I'm just, in practicality, we never make theta 0 equals to 0. It's just that to give you mathematic derivation, make the derivative easier, I'm just assuming my best line is passing from theta 0 equals to 0. For example, this is how my best line is passing for time being. So now theta 0 part is removed here. Now you let's understand this algorithm. I want to pass one line. So before coming up to this formula, this part is already understood to you. What this part is saying, this part is saying, okay, boss, pass a line from these points as theta is nothing is with the y hat. Take the difference, right? The way we did it here. Uh, take the difference, square it, square it, and do the sum, right? That's it. Take the squares, make these differences. This is y hat minus y. Make the squares and sum up all, right? So best line would be what? For which these sum is lesser. The lesser the sum, better the line. Eventually, I would be having infinite n lines. Each would be having this sum, right? Which is my best line, which is having this sum lesser. So eventually, this whole boils down to a matrix. If somehow we are able to reduce that matrix, we're gonna get the best line. 1 upon 2m is nothing but the average. 1 by 2 you will see later. Ignore this part. Main, and this is summation. Adding all the. So if I explain this line, this would be something written as, so this is nothing, this is something as y1, uh, y 1 minute, y hat 1, y1 square square plus y hat 2 minus y hat 2 means second data point, second line, y2 square plus dot dot dot. Do it for all the data points. So I denote data points by n, y hat n minus yn square, right? We sum up all. do the sum. This is basically kind of average, and divide with number of data points. Number of data points is m, just number of data points. So this is what is written in this equation. I already told you that what our goal is to find, goal is to reduce this sum, the line for which the sum is lesser, that is our best set of thetas. So our goal is to minimize this this function. This function is nothing but the mean. This is mean squared error. This is what? Squared error. You are calculating the mean of squared error. So we introduce one new term which is known as mean squared error, right? And the thing, uh, uh, you mentioned the one of you mentioned this absolute. So actually I'm not able to see the name, so I'm just saying one of you who mentioned this thing, absolute, that is known as mean absolute error. So indeed that's a term in machine learning. We're gonna see it later. But for right now, for the current scenario, we coined a term, we discussed the term mean squared error. This is the function. In this case, we are denoting a term which we are calling it as j theta, right? Theta is what? It says this is a function which takes thetas and give you this value, which is mean squared error. And we call this term as, cost function, right? Now this is the second term. Now we just show cost function. Always you will, now this becomes the basis of in future. Each machine learning algorithm will be having one cost function, and that we're gonna drive every time. This is the cost function for linear regression. If first we create the hypothesis, what we want to achieve, we create a cost function. Once we create the cost function, our goal is to minimize the cost function here. And before going this theoretically, I practically explained that why we want to minimize the cost function. Why? Because those would be the lesser the sum of the squared error, better is the line, because that line is more closer to the points overall, right? This is what we want to achieve. Is that clear till now?
Yes, yeah.
Okay, so
Yes.
so this is what you mentioned. Everything is same, so we are going together. Nothing has changed. We calculated the differences. Now we want to minimize these differences. We cannot minimize each difference because they are lakhs of point. We want a best fitted line which takes care of all the points. So therefore we squared them. Why we squared them, we discuss, and we take the mean. It's easier to work with the mean. So this becomes a cost function. So one thing which I mentioned, this is how all the algorithm works. How the algorithm works, especially supervised algorithm. We come up with an objective, what we want to do. Then we discuss its mathematical, mathematical way of finding some function. That function is known as cost function. Sometimes you will also see it as loss function. Loss is a term generally used in mathematics most of the time, which is nothing but the error. Loss means actual minus predicted. Difference between this. What is the loss? It could, so this is just mostly let's stick with the cost function. So this is the cost function, and finally, in this case, practically our goal is to minimize this cost function. If somehow we are able to minimize this cost function, we would be getting the best line. Now see how. For this, I want to explain this example here. So, mm, I'll take first very simple example, then I'll move to a 3D example, and then things will start becoming a little complex, but more easier from now because you have already kind of covered the basis. So let's explain this thing in 5 minutes here. Come to the bar, right? Now this is gonna be a different set of line. Let's make it a little better. Okay, suppose this is the set of, this is a line. This is theta 1 values. ranging from, it could be -10, -1000, indefinite, minus infinity to infinity. This is the theta 1 line, for example. What is theta 1? Theta 1 is nothing but the coefficient associated with y hat. So before doing that, let's see one thing, otherwise it would be difficult. Y hat, right? Let's explore this algorithm. Q1 dot x1. This is my y hat, right? Y actual value is y. What we mentioned, take the y hat value, which is nothing but q1 dot x1 minus y square of all. This is what we are discussing here, right? Error of, and then what we mentioned, summation here. We do summation of 1 by 2m. This is my cost function, right? Summation. So basically all the points, all the green parts which we see. Now let's see Q1 here. I draw a line here, Q1. Now suppose from universal, again, from the universal space of Q1, which could be exist, I choose all Q1 values and then I put Q1 values here. I already got X1. I already got Y. I calculate this thing, cost function, and plot it here. So basically, I am just plotting a cost function here with respect to theta 1. Now, initially, when your theta 1 is very bad, just some, your theta 1 is very bad, what will happen? Cost will be huge. So some theta 1 cost will be huge. Of course, that makes sense. Your theta, for example, if your theta 1 is very bad, I mean not appropriately coming to graph. This is my graph. I choose some theta 1 for which my line goes like that, out very, very far away from point. That's a very theta 1. For this theta 1, the squared error would be huge. I mean, you see, this is the squared error. Actuals were somewhat here. This is a squared error. So pretty plain mathematics. Since theta 1 is the part of this y hat, if theta 1 is very bad, the difference is gonna be huge. So overall cost value gonna be huge. So it would be somewhere. Now what I do, somebody told me some better theta, my cost function will value will reduce. So somebody, some person who knows, I mean some kind of astrologer, he start telling me correct theta ones. So my value theta cost function will start reducing. Right. Now one point will come up here when we are not actual, but we are reaches to that set of theta one for which we are getting the very lesser cost value. Then what happen if we start moving away? The cost value will start again moving up, because first you are coming closer to that theta one. Now you are going away from the theta one. It's just a square, so works like same. It will penalty for both left side, right side. The cost will start function. Somehow this is my, the graph of Q1 J theta 1. Now looking at that, you will agree that what is my ideal Q1? My ideal Q1 is somewhere at this point, right? So what I want the local minima point. I want that theta 1 for which the value of cost function is lesser, lesser among all. This we already see. In general, which is this is nothing but the local minima, right? So somehow give me some mathematics way so that I can find this local minima. If I am able to find this local minima, I will get the theta 1. So now my problem boils down to find the local minima. So now how I can do that? Now, let's rephrase it. Some good way of finding the minima. Not use the word local, finding the minima. Minima means the point at which we get the lesser error. This is what we are discussing for last 15 minutes. We want lesser cost value, lesser squared sum. This is nothing but a minima. Again repeated, as we are very, very far away from theta 1, this sum would be huge. So the error would be huge. But as we start moving towards theta 1, the error would reduce. So these points. At some point we would be closer to the theta 1, but again we start moving away from q1. Since this is squared error, we get this graph. So we surpass the actual the closest theta 1, but this is how we want, and this exists at the minima. So now some way of finding the minima. Now if we go to the 11th mathematics, if and you now you can, I mean, the best way of finding the minima is by doing the differentiation. This is how differentiation works. Differentiation. So if you do the differentiation of y with respect to what, x, they will give you, for example, the people who mhm,
Zero. It will give zero.
differentiation y with respect to, this is my equation, y equals to mx plus c. So mx plus c, it will not give zero, it will give. So if you differentiate, the people who do not know differentiation or forget, that's okay. So if this is a equation, I do the differentiation of this y with respect to x, the output would be, intercepts are constant. So the differentiation of intercepts are always zeros. dy by dx, the differentiation of mx, x will remove, will always be m. So m is what? So m would be your theta 1. So what we want? We want our differentiation equals to 0. So when you differentiate something to 0, it means you want that theta 1 to be closer to the minima, and this is how you will get the best theta 0, theta 1, in this case theta 1. So for this, two things are new. If you have not studied, first thing, this is plain understandable. Why? Because the equation is very simple. Just y equals q1 x1 minus y. We have our q1 is initially very bad. Ultimately, we find best q1, but we do not know. So, take an example. Some astrologer come up. He starts saying that take q1 equals to this. So we put q1 here, but that q1 was very bad. So we got a very high error. Therefore, you see is very high upper side. But we then what we see, okay, let's reduce q1 little bit. So we reduce it little bit. So it becomes the here. Error is reduced because you are moving your q1, this q1, here the q1 is this point. But then you move q1 from here to here on some value. Set this was 3, now move 2.5. The error is further reduced. Now you moved it from 2.5 to 2, for example. So error is reduced. At this point, the error was say 1. But now we start, it's somewhere here. Now we are going far away from q1. The error start increasing because this is a square function. We keep on increasing. So our graphs will become like this. So this is a graph. And this graph, this is a quadratic graph. And the minima is always calculated with the help of differentiation. So if you want to do not give much thought, then always differentiate. A function's minima can always be found with the help of differentiation, and this is what differentiation do. So here we will differentiate this cost function with respect to x1 equals to 0. So when you differentiate, it will give you q1, and finally you will get this value of q1, for which, and by differentiation. Now, very good point here, and now things will start making sense here. Practically, from mathematics term, if this is the graph, differentiation is nothing but a line, a kind of an angle. At this point, the angle is 0 degree. You know, this angle is 0 degree with respect to this point. This is kind of a tangent.
Hello.
Hello.
Raj, sorry, can we have a short break for 5 minutes?
Okay, fine. So okay, perfect. So I mean, guys, as of now, let's summarize till here. Uh, we got the cost function. We want to reduce this cost. We want to reduce this cost function. Therefore, we want some way. We discuss this example. I'll continue from the same point here. Right? Let's meet up after 5 minutes. 8:42 it is.
Okay.
We will yeah, we will connect at 8:50.
Okay.
Okay. Yeah. Okay, let's wait 1 minute.
Yeah, we can start.
Okay, perfect. So let's summarize the very first R. Uh, this, this is what we are working. We are working on to find the best line, for example, and that we can achieve finding the best set of theta 0, theta 1. We see. Now we've sum up that if somehow we are able to reduce, sum up able to find the square of the differences, actual differences between the actuals and the predicted values, then that would be give us the best line. These kind of formation, in this case, this is a mean squared error. This is known as cost function. So our goal is to minimize the cost function. This is a set of how a machine learning algorithm is devised. This is general way of doing for all the algorithms, other algorithms as well. Somehow you have to find the cost function. In this case, it is a mean squared error. So goal is to reduce the j, minimize j. So for that, what I created an example. The example was that we put all the thetas one here. That theta one will give me some error. I will keep moving the thetas in the direction such that the error decreases. At some point of when the theta will arrive such that the cost is very lesser. This is our prospect. This is the prospective theta one. But however, if we start moving away from these points, the curve will start going upward direction. Means the error is now increasing. Somehow we want some mechanism to find this value of theta one. Now coming to the mathematical differentiation, this is the graph. This is the this is the tangent. Tangent, tangent is nothing but the line which gives you the slope equals to 0. The line which just touches the data point here. So this minima can be calculated by taking the differentiation. Differentiation gives you slope. So this is nothing I am writing here. Differentiation gives you slope. So differentiation of here by head, which is nothing but theta 1 x1, right? This will give you the equals to 0 will give you the slope. So when you this slope, and we know at the local minima, because we know that here at the local minima, this point, the slope is 0. Therefore, we are equating this thing with 0 because the tangent is 0 or slope is 0. So when you do that, you do dy by dx1, this will give you some q1. And finally, this is how you will get the best set of q1.
Hello.
Yeah.
So,
Please.
like, we have taken that deep as a minima, I could say. So, maybe that can be some local dip, and we may have some more like next dip, which is like little bit
Definitely.
down than previous.
Definitely.
Then how it
Definitely.
might.
Yeah. Good question. Again, coming to that part, y1. Let me fully complete this part. Yeah. Perfect. This is we gonna do, and this will give me the best value of q1. So again, let me repeat it, guys. This is the graph of cost function. Cost function started decreasing as we move q1 closer to the actual, not actual, the best q1. But if we somehow move further ahead, the cost value will start increasing because it is a square function, quadratic. So somehow we want to find this thing. Now then we thought how we can do that. So we see at this point the minima lies where the tangent is 0. Tangent is where the tangent lies. Tangent is what? Nothing but the slope is 0. So here the slope is 0. So how you can find the slope? You can find the slope with the help of taking the differentiation. Differentiation always give a tangent at the local minima. Now when I equate it to 0, because slope is 0, I get the best value of q1 because y1 is known, x1 is known, we are doing d upon dy. Then when I equate this thing on the right, we get the q1. Now he asks that there could be the cases where, I mean, there could be local minimas. So I'll come to this example. Let me. Okay. So by taking the differentiation of the cost function and equating it to the 0, it will give you the value of d1. But this is the ideal case. This is now not how the thing works. Practicality. Practicality. Now consider the example. I explained you with keeping theta 0 equals to 0, assuming that line passes from 0. But this is not the case. This is not the case. This not happens. So what happened if I got theta 0 and theta 1? So what happened here? Just a moment. Yeah, take this part. Would be easier for me. You know, take this graph. I want to draw something. Copy, put it into Excel draw. It is right. Make it big. Okay, let's understand this thing. Okay, what it says? It says that now now we are dealing with y equals to, now my equation is now somehow y hat is equals to theta 1 dot x1 plus x0 plus theta 0 not x0, right? So this is two coefficient associated, so you are not the cost function gonna look like this way. If it is a one line, if it's just a single variable, your cost function, how it was looking, it was just this way: one value of q1, one value of j, cost function, mean squared error. But when we also got q1 here, we got q0, the cost function would be in the shape of pole, right? Now suppose you take this value of q1, which is say for example 9, you take value of q0, which is somewhat equals to minus 12. For these values, my cost is lies here. Now if by any chance we would have taken q1 equals to here this value, and q0 basically the intercept equals to 0, we would have end up somewhere here, j value. So these are the different sets of value lies in the 2D for two variable q0 q1. Now so the just you asked me that there could be the cases that we could have started here, or we could have started here, we could have started here, or we could have started here. Ultimately our goal, so there could be many cases. For example, we by changing the values of q1 q1 q0, we could descend and we could reach local minima like this way. This is one set of way. If we would have started, our goal would be to reach the local minima, and we would have taken some path. These are the values of j theta, j cost function getting changed by changing the value of q1 q0. So arbitrarily take some value, cost will decrease. So there are different ways you could have started, right? Now consider a case, consider a case and this part is clear, guys. I mean, if it was just q1, so it's just one variable, so we get a quadratic in a 2D space. But here we have q1 and q0, so we have two variables on which j cost function is dependent. Therefore we are getting a quadratic bowl, a quadratic plane. It's just that you increase one dimension, so dimension increases. Ultimately it is just nothing but q1 equals to, and this is just kind of this thing. Here we were trying to reach the minima, this point. Now here also, irrespective of where we start, the which pair of q1 q0 start, our goal will always be lie to reach the minima, the minima part. This is what we want, I want to convey here, that now if this would have been cases that it is q1 x1 q0 plus q2 x2, one more feature, so that's a 3D, so I cannot draw a 3D quadratic bowl. But thing lies that way. I mean, even if you increase the dimensions, the goal will always to reach the minima. How you reach the minima? By choosing some q1 q0 q2 for which value of mean squared error is lesser. And how you can make them lesser? You can do it by taking that differentiation. Right now, the question which was asked to me is that there could be the cases, there could be the cases of this cost function you see this way, but they are q1 q0, there are many things. Let me come up ahead. Okay, so what, so now suppose this is a again set of q0, and now start following with me. This is q0 q1. What we do by changing the q0 q1, these are different sets of value of j cost function. For example, if you would have choose q0 as zero point 0.6, q1 at 0.6, you could have end up somewhere here. If you have chosen very bad q1 somewhere here, very bad q0, you would have end up at this here. So this is called as contour of the cost function. Contour is the word which is used to tell or represent such kind of planes. And these red colors mean the error is huge. Therefore, these are plateau. I mean, kind of hills. Blue are the lower ones. Now, suppose I started I started with Q0 equals to zero point 0.7, or uh, and then I started with Q1 equals to zero point 0.6. So I started somewhere here. So this is one way I could have chosen. I could have descend like this way. Suppose by changing the values, I could have end up here, right? Now, one of you started with different set. You started with zero point 0.3 and roughly you started from here. So you could have end up, you know, by reducing the j, by reducing the taking the different value q0, q1, you could have end up here. You could have your model will give that, okay, this is the minima. So you see the term he mentioned, that local minima. I mean, every point is a minima, right? Now there are two terms: global minima, local minima. Global minima means the the one point for which we get the lowest value of theta 0, theta 1, choosing theta 0, theta 1. Local minima means, local minima says that I am the minima in this region. In this region, this is the minima. In this region, this is the minima. In this region, this is the minima. So based on model training, you could have end up by this minima, this minima, and this minima. So he was asking that what will happen if you end up in some local minima. So that's something which I discuss later. But as of now, our question was to find the best set of theta 0, theta 1, theta 2 maybe. This will plainly come up by the concept of taking the derivative, right? So for example, what I mentioned, I started here. I change the value, vary the value of Q0, Q1, I end up here. So, okay, after that, my cost function might increases. So I will say, okay, this is the best set of Q1, Q0, Q1. That's okay. I mean, linear, this is just prediction. So you are getting your best set by using this Q0, Q1. But you would have chosen, you would have moved in this direction. Then you could have ended somewhere here. So for this region, you reach the local minima here. So this will give you value of Q0, Q1. This becomes your one line. Of course, this line is better because you reached at a further local minima, right? So there could be n number of cases, right? There could be n lines. How you come up with the fact that I reach the global minima rather than local minima? This becomes our last and final output of the linear regression. Let me boil down all the stuff again here. So initially we discussed that, okay, uh, I want to come up with some y hat. Then I decided, okay, mean squared error is one way. Then I decided, okay, take the derivative. By taking the derivative, I will get the minima. I will get the minima. But now we never deal with just one variable. We deals with n number of variables. So it's just not plain, plain quadratic equation, for which there exists one minima. We are dealing with what? A kind of we are dealing with a kind of a cost function which varies on different values of theta 0. Therefore, we need to reach the global minima rather than local minima. This is solved by a algorithm on which linear regression depends, which is called as gradient descent, right? So this is gonna be our next and final objective of linear regression. So in
Uh,
simple, if Mhm.
Raj, I might be confused. So, uh, please correct if my understanding is wrong somewhere.
Yeah, please stop me anytime. Yeah.
Um, we are trying to find the minima because at that point it will be the y hat will be as close to y. Is that correct? First question.
Uh,
Or
partially. I want to calculate minima because at this minima the cost function would be lesser among all. Lesser the cost function means what I mentioned, lesser the cost function, better is the fitted line, right? So
right.
yeah, your final ultimate goal is achieved, but the correct explanation is that I want to find the minima because for the minima the cost function is lesser. Lesser the cost function value, better is the line. Got it?
Mm,
This is cost function. Let's not confuse
yeah.
by the
Yeah.
mathematics,
Yeah.
right? These are the green lines.
Yeah.
We want the best line would be for which the sum of these lines are lesser,
Correct. Correct.
right? This is nothing but cost function, right?
Mhm.
This is cost function here. This thing q1 x1 minus y square. This is j. So if somehow you say that okay, for line 1, for theta 1, this is the lowest value, it means you already reached the best fitted line, right?
Right.
and, and best fitted line is always achieved in this 2D by taking the derivative of the cost function, because derivative always takes us to the lower local minima, lowest minima, right?
Okay. Okay.
Now this is okay, I mean this is a very good situation we are done, but we never stay with just one variable, right? So our cost function in practical looks like what I mentioned here. This is how my cost function actually looks like, because there are, see,
Yeah. Yeah.
between 0 to 1 there are infinite value of q0, 0.001, 0.002, 0.51. Similarly here, 0.61, 0.62,
Right.
likewise.
Right.
So there exists, different set of j's here, and this is
Right.
how it looks like, right? So
No,
this
my confusion is basically where the minima is going on the negative side. So I can't comprehend how that would work is something I'm
minima
confused.
going
Maybe
on where,
on the negative side. So for example, if you open
uh-huh,
the can
just
you
a
open
moment.
the diagram again? The one that we were seeing, the
Yeah,
3D,
this one,
the
3D one.
3D one. Yeah, yeah.
Okay, okay, just a moment. Yeah, this one.
Here, yeah. Here, if we see the minima is no, the one before.
Mm-hmm.
The local minimas are going somewhere around -2 or -1 something.
Hmm.
So
So this
that's
this this is, yeah, I so this case is that this is the graph.
yeah, yeah.
This is a graph -1, -2, -3. In our case it will never go between 0, because our is mean squared error, right?
Right. That's what.
Right.
Yeah,
Yeah, yeah.
that's
So
what.
this is in general graph I taken from somewhere to
Okay.
differentiate.
So
Okay.
so in our case, we will never go down
No, no, no.
below zero. But yeah, okay, understood then. Yeah,
And
that's
yeah,
what.
so
That's what.
and very well catched here, I mean caught. uh, I will remove these things here. So in our case it will not, but some cases the cost function can be negative, right? So that's okay.
Yeah,
Fine.
yeah.
Perfect.
Hello,
So,
hello,
yeah, yeah.
hello. But how cost function will be negative? Because here actually what we are looking that when our slope is going to be zero, okay. When we are saying that our slope is zero, that means we are assuming that at least we found the local minimum. Then why it should go to the negative? And even
Okay.
if it gets the negative, I don't think it matter because we are looking for the zero, means where the
Hmm.
slope getting
Yeah.
zero.
Okay. Okay.
So
I'll
it
answer first question.
doesn't matter, I guess.
Okay. That, yeah, that's okay. But I'll answer if somehow I'm wrong, but somehow if my cost function is a cube,
Yeah, yeah.
then it could be negative. My cost function can
Yeah,
be negative.
yeah, for sure it
It's a,
will, it can go in
it
negative
can negative
also, but
direction.
we are looking for zero,
But
correct?
yeah, your point is valid. So, but I answered his question. He might be confusing it with the square function here. Therefore, yeah, in this squared error, no, it cannot be below 0. But this doesn't
Oh,
matter, because eventually the slope will always, the tangent will always be 0, right?
Yeah,
So it's
slope
okay.
can be
My
zero or
I'm
negative.
just I just need to focus. No, where is my minima? Now here you can see there are multiple minimas. So this is one local minima. This is one local minima. This is one local minima. For example, this is also a local minima at the very corner side. If I started somewhere here, I end up here. So this is not a line best fitted. My best fitted line somewhere lies here. So
Yeah.
what is the best way, or basically the way to reach, maybe started from any point here. 99% you will reach here, but some cases are the differentiate. But if you some I started from here, how everybody or every model try to reach here, this is the goal, and this is achieved with an algorithm called as gradient descent. And gradient descent becomes, the crux of a linear regression. So if I now summarize everything in just four or five statements, thing is, I get an objective I apply linear regression, I created a y hat, and then I find that okay, The best line would be where I get the squared error lesser. So for that, I calculate the cost function, which is nothing but the mean of squared error. And then I figured out, okay, on experimentation done on 2D level, the best theta 1 can be achieved by putting derivative of cost function equals to 0, because derivative of a 2D always derivative will always gives you minima. So we in mathematics, the current terminology is first differentials gives you the local minima, right? First differential means dy by dx. D square by dx square would be second differentiation. That is Hessian, but let's leave that. First difference derivative will always give you the minima. Now here, if you took the derivative, you will get this minima. If you take the derivative somewhere here, you will get this minima. Now problem lies is that we are dealing with a very different value of q1 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 q0. I could end up here, I could end up on that side, which is not right, I mean. So we want some algorithm which properly guide us to reach, irrespective of where I start, it guide us to reach to the global minima. That's the goal, or closer to the global minima. If I started here, I might end up here, that's okay, still my model is better as compared to I ended up here. So this is my goal, and how I'm going to achieve that, the last point, which is the gradient descent. So we call this term as gradient descent, right? So is there any optimal or better way to update parameters instead of just randomly updating it? So I do not, I mean, see, we are training on thousands of points. I cannot manually change the or write a for loop. Okay, say somebody tell me, okay, just take for loop. If just is two variable, just write double for loop, nested for loop, iterate on all the theta 0, theta 1, and take the one for which j equals to j is lower. We could have done on two variable. But if there are 100 coefficients, the complexity would be n raised to power 100, and cannot be achievable at any point of time, even with the GPUs, etc. So we want some intelligent way of reaching, finding the best set of theta 0, theta 1. How we gonna do that? We gonna do that with the help of gradient descent algorithm. Now guys, so I think it's better to start this algorithm in the next session, because eventually this will so it's good to brush up, from starting to this thing. But I'll explain you gradient descent algorithm in next session, or maybe either we can take one session in this week, the way you mentioned to take it on some Friday or Thursday. We can plan that as well, maybe Thursday somewhere. So this way, we will end up our linear regression, because this is a very important part, and you will see gradient descent algorithm in multiple places, not just in linear regression. As the name suggests, gradient. Gradient is what? Gradient is the, as of now, the simple term in layman is not the slope, but just simple term, consider it as a slope. So I want to descend on the lower part. So they are sometimes called as gradient ascent. When you, in gradient ascent, you move ahead. In gradient ascent, you climb up. In gradient descent, you climb down. So this is the terminologies for which this name comes up. I want to descend in the direction of slope, right? So this is the algorithm. I'm gonna start with the same 2D, and then we're gonna see how its derivative come up, and then we're gonna do it on a more than two variable, right? It's very easier because most of the part is done. You already understood how the derivative works. Basis is done. How derivatives and all the data points helps us to calculate gradient descent algorithm, that we're gonna see in our next class. So once we able to find the descent algorithm, we now do not need to manually get, put some theta 0, theta 1 into the theta 2, theta 3. The gradient descent algorithm will eventually go do it for us. And eventually after that, which we call as machine learning model training, in linear regression, machine learning model training is nothing but the gradient descent algorithm for now. Later I will give, there's one more faster way. You Somebody must have heard of, that is known as Newton's method. Some statistical way of doing linear regression use Newton's method. Underlying concept remains same. So gradient descent helps us solve this problem. It helps us solve the problem that irrespective of theta 0, theta 1 you start, irrespective of what you will, the gradient descent algorithm will try to reach us to the global minima. Global minima is the minima among all the local minimas, which in the graph looks like this point to me. This is my goal. I started from here, I should reach here. I started from here, I should reach here. Even I started from here, it should ideally traverse the path, going this path. It will not climb up. If it would climb up, that would be gradient ascent. No, it will move, it will start moving slowly, slowly, and then it will try to reach at the this is what gradient descent does, and this is we're gonna see in our next class. So finally, if we able to understand the gradient descent, our linear regression algorithms will end, and then we will take some examples and a practical session how to code it with the help of machine learning libraries, and then you will see the practical implication of all these algorithms there. So I think, does it make sense, guys, to take it in the next class?
Yes.
Yeah. So for now, what I'll suggest, take the example which I mentioned here. Please just have a look. I'll share this slide. PMT. Yeah. Let's take this example. This is the main crux. Basically, there could be n lines. The best thing as of now we could come up is that somehow find the lines for which the squared errors is lesser. So that gives us the pointer towards the cost function, which is a mean squared error, which I see. 2D example you understood. In 2D, if we take a derivative, first derivative always gives the slope, and this is what we want, because at the slope lies the lowest value of j theta 1. If I put it equals to 0, because slope is 0, I will get the theta 1. In practical scenario, you will not do it manually. There are libraries already doing this work for you. There are libraries in Python, but this is must to understand, right? This is our final summary. We write a hypothesis, we find the parameters, we find the cost function. We need to minimize this thing to find the best value of theta 0, theta 1. How you can do that? Overall answer, we can do that with the help of gradient ascent algorithm. Inherently, a gradient descent algorithm works by working on the derivatives that we're gonna see. So I initially explained the derivative part to you, but same concept we're gonna see again next class in gradient descent. So once you understand, we would be done with the linear regression algorithms, guys. Yeah, so that's how let's come up with the questions now. Or we have 10 minutes. If somebody wants me to repeat, I can repeat some stuff again.
So here in cost function, we have not seen the theta zero, correct?
Uh, in first case, because I wanted to bring to understand you, I wanted to bring it, 2D.
Yeah.
I
But you are
used theta
saying that simultaneously we are wearing this to find the local minima, correct?
yeah, always. It's not just not that you vary theta 0, theta 1. All the variations will happen simultaneously. Otherwise, this problem will take a lot and lot of time. How you do that? We're gonna see in
Mhm.
gradient descent algorithm.
Next,
So they
that
are
is
two
okay.
way. Yeah.
Mm.
So they
I
are way
see.
of
Yeah.
doing that. Yeah,
Nice.
stochastic way where when you work on one by one, then they are grouping way where you work on all the theta simultaneously. Right. But
Okay.
yeah,
Thank you.
this
Yeah.
so yeah. So with the help of gradient ascent algorithm, you will reach to the global minima. And once you reach the global minima, you are already taking the derivatives. They will give you the value of theta 0, theta 1. So ideally, we work with the partial derivatives, because then you calculate derivative. Suppose this is the cost function, and we got theta 0, theta 1, theta 2. So we were calculating derivative of derivative of cost function with respect to theta 1, derivative of cost function with respect to theta 2, and we will equate everything to 0. So by doing that, you will get the value of theta 1, theta 2. That will happen, right? And this way, and this happens parallelly. So that's okay. Partial derivatives. So what I suggest, everyone, just refer this part, try to understand, just maybe chat gpt somewhere, just see how taking a derivative, I already explained, but just search the relation of derivatives, finding the value, lowest value, with the help of derivatives and concept of partial derivatives. These knowledge of derivatives and partial derivatives will be helpful for me to explain the gradient descent. But again, I'll keep the things in very simple layman terms, and then technical later. But yeah. So I hope, guys, let's end this for today's session. Our goal would be to reach from wherever you start. This means again, which theta 0, theta 1 you start. We want to reach to the global minima. I mean, somewhere here, not exactly here, maybe somewhere here. So if you reach even closer to this point, it means you have reduced the error a lot, and that reduction in the lowest cost function will points to me the best fitted lines, right? So in practical, you see each data point on this plane is a line. Each point, so you can see this is the infinite numbers of line existing here. So each line is a line which fits the data point. I want best fitted line with somewhat light here, the lowest j theta. So this we see in next class how to do that.
Raj,
Hmm.
let me summarize the steps that I've understood so far.
Yes,
So
Pratik,
what
please.
we'll
Yeah.
do is first we'll have some inputs, some outputs. Okay. From
Hmm.
the input and output, we will try to derive a linear equation perhaps, such as y is equal to mx plus c. And then what we'll do is we will create root mean the mean square error values for for each input, I
Square
suppose.
mean error, squared. So correct term is aggregation of the squared error.
Okay, aggregation of
So,
squared error
like,
for each
but
input will do that. Or
yeah, and perfect. But I mean, are you okay with the fact that why we are doing the aggregation,
yes,
right?
yes, yes, that I
Okay,
understood. Yes,
perfect.
because
Okay.
because
Mm.
the difference may cancel out each other. We don't want that effect. That's why we are squaring it to ensure that the
Yeah,
values which are below the line and above the line are both considered in all cases, in
and
cases,
yeah, and we are
even if they are same.
aggregating.
Okay, yeah,
Yeah, we are aggregating because we want to consider a best fit line among all the points. The example
correct,
which I give you here, that if
correct.
we consider this point, my value will change.
Correct.
Okay,
And then
and
we what we'll do is we'll have one new array, for example, with all the aggravated square errors, right? And then from that array, we are trying to now find out the minima.
so
So,
so
for
you would,
example, right now I'm just considering the 2D thing. That's why I've
yeah, yeah,
said array.
take 2D,
Maybe,
yeah,
uh, once we move to 3D, maybe it will be array of multiple dimension, and through
hmm,
which we will be finding out the
perfect.
minimum. And then when we what we call local minimize, for example, we have taken a group of numbers or set of values, the minimum of which will be minima, and then global will be the minimum of all values, right? So
Perfect. Yeah. Mm.
yeah, so I'm just trying to
Yeah.
think of
s-
the steps that we are trying to do here,
Yeah.
right?
So perfect. Just one line I want to add, Pratik, here is that the line which you mentioned, you take the array.
Mm-hmm.
So that thing eventually would be done by the gradient descent algorithm. For that, you do not
Okay.
need to, then array could be, you can take an infinite value of q0, q1, right?
Mm-hmm.
So
Mm-hmm.
we should write the code, machine learning code, in such a way that it automatically takes the q0, q1 value over the iteration. So that part would be done by the gradient descent algorithm. It will
Okay.
by itself take some q0, q1 automatically, using the system automatically. But it will happen by gradient descent. It will
Yeah.
change it will keep on changing the value of q0, q1 until you reach the local global minima, right?
Right. Okay.
That's what gradient descent will does, and that is what once this has happened, then we say that we have achieved a state of machine learning using gradient descent and
Okay.
and overall by a help of linear regression.
Okay. Understood.
So guys, same concept will apply. We're gonna see later. Same algorithm applies if you go with the polynomial regression. Is the only difference is how the derivative works. Just that derivative works on linear regression. There the derivatives would be working on uh, polynomial regression, polynomial equation. In polynomial equation, it's mostly partial derivatives. So for example, if x1 into x2 is multiplied together, you have to take the derivative with respect to x1 first, then x2. It's just about mathematics. But overall the fundamentals remain same, right? So so yeah, just keep things very simple. Always try to understand with 1D example. Once 1D is explained, understandable, then we move it to a global level for x2, x3, x4. So yeah, we already with the time. Please do revise it once, and then next class we will. So what is the agenda next class? We will I will try to complete this in the very first hour, and the second hour I will demonstrate a machine learning linear regression problem with actual examples of thousands of points. We're gonna see how we do it in how we're gonna do it using machine learning libraries. I will do it practically, and once you are able to understand that, you can apply the same logic, etc., on different business objectives, right? So yeah, guys, that's it for today. If no question, we can close for the day. Thanks for your presence. Yeah.
Yeah. Thank you, Raj. Thank
Thank
you.
you. Bye.
Bye.
Thank you.
Thank you.